Hello everyone and welcome back to another video. Today I'd like to talk about 3D plotting in Matlab. Now during this video we're going to build off many of the topics and concepts presented previously in my 2D plotting in Matlab videos. So if you haven't watched this yet, please stop and visit the link in the description. So in terms of an agenda, we'll cover two distinct classes of 3D plotting in Matlab. The first is 3D plotting using lines and points using functions like plot3 and scatter3. The second class of 3D plotting is 3D surfaces. However, before looking at how to implement this in MATLAB, we'll take a step back and consider the general concept of how to generate a 3D surface on a computer. Once we have this concept down, we'll take a look at tools in MATLAB to enable this workflow such as patch, meshgrid, surf, contour, and surfc. Finally, we'll look at combining 3D surfaces and lines to generate some very interesting and descriptive graphics. So, if all of that sounds good to you, let's jump over to MATLAB and dive in. Alright, so let's go ahead and start ourselves a new script here in MATLAB. Maybe we'll say the point of this is to investigate 3D plotting in MATLAB. We'll start out with our normal clear CLC close all. And maybe to start here, let's go ahead and how about review 2D plotting in MATLAB, right? If you remember here, all you're doing with 2D plotting here is defining a whole series of points, and then MATLAB will then connect those points with straight lines. So for example, if I want to make a line going from the point 1, 2 to the point 2, 3 here, what I could do is I could define some x values to be the x value of the first point, the x value of the second point. And then I can define a vector y, which is the y location of the first point and the y location of the second point here. So if I were to go ahead and start a new figure and use the plot command on this, and maybe let's pretty up the plot here with some labels, and maybe we'll turn on the grid, we see that all this is going to do here is draw a straight line from the point 1, 2 to the point 2, 3. So again, if we just run this, and I'll change my folder to this location, that's exactly what we get, right? We get a straight line from the point 1, 2 going to the point 2, 3. So the extension to this concept into 3D plotting is actually very, very simple. So instead of specifying a vector of x and y locations, we also need to specify the z locations for these points, right? It's now going to be a point in 3 dimensions instead of point of 2 dimensions. So let's go ahead and say z, how about 1, 3? So now what I would like to do is I would like to make a straight line going from a point at coordinate 1, 2, 1 going to the point at coordinate 2, 3, 3. So all I need to now do is pass in z, and now instead of calling plot, I'm going to call plot3. Plot3 is the three-dimensional version of the plot command here. And again, all I maybe should need to do now is add a z label, because now there's going to be an x, y, and z axis. And if I run this, we see that we get what is a three-dimensional plot going from the point of 1, 2, 1, going to the location of 2, 3, 3. So here's my three-dimensional plot. The one new feature here in MATLAB that you may want to investigate here now with a three-dimensional plot is there's this little button up here which looks like a little rotating arrow around an object. If you click on this and come here to the plot, you can now grab and drag this. You can see you can move the viewpoint here. So this is very helpful for understanding what a three-dimensional object in MATLAB looks like. So this is pretty helpful. Why don't we come back here and we could even modify this. We saw earlier that all you need to do here is if you want to add more points is just tack on additional values. So let's say I want the line to go to a third location, maybe located at the coordinate 5, 4, 0. So all I need to do is add a 5, a 4, and a 0 here. Oops, let me get this white space a little bit better. Run this again, and we see now we've got a multi-part line that goes to 2 coordinates. So this is looking great. You know, we can even expand this if we want here. How about let's make this a little bit more interesting than just, 2 straight lines here. Let's comment out this section of code here, and all we need to do is just make x, y, and z a little bit more complicated. So you know what I'm going to first do? Let's create a vector to represent maybe time. I don't know. Let's do it like this, 3 pi, and maybe let's use 30 segments here. And then I could say that the x values here is, how about 3 times cosine of t, whoops, The y values are, how about 1 times sine of t, and the z values are, how about 0.01 times t squared here. So all we're doing right now is now we're going to try to draw like it'll effectively be like an upward rising helix, right? So if I look at this, you see that, yep, we actually do get an ellipse, and it's this helical shape. Well, actually, you know, and it's supposed to be ellipsoid here, but you can kind of tell here that it doesn't look like an ellipse. It looks more like a circle here. That's because the axes are not scaled appropriately. You'll see that the x and the y and the z axes, they all use different delineation. So basically the axis is not square. So one quick modification that if we wanted to fix that, we could just go ahead and say axis equal. And if we run this again, we should basically get a similar result, but now all the axes are equal. So now if we look at this from the top, it does look like an ellipse with semi-major axis 3, semi-minor axis 1, and the z-axis should also be appropriate. So here we go. So this is how we can use the plot3 command. It's basically like the plot command, except it's in 3 dimensions here. I want to show you another function that might be helpful. How about let's take a look at the scatter function here. So I'll start a new figure here, or excuse me, the scatter3. So scatter3 is very, very similar. All you do is you pass it the exact same arguments here. And I'll tell you what, let's go ahead and, well, I'll grab the rest of these parameters as well here. And if you run this, you see we get two figures here. And you can see all scatter3 does is it plots all of the points as little blue circles here instead of connecting them with straight lines. You know, you can actually recreate the effects of scatter3 yourself using plot3. We saw earlier with the plot command that you can specify how this line looks like. So instead of using a line, we could say let's use magenta circles instead of a line here. So what this will do here is now, don't these two look very, very similar, right? Figure 1 is using plot3 here just to draw magenta circles. Scatter3 is just drawing blue circles. So really, I never even bother with scatter3. So I'm just going to comment that out because you can do the same things by yourself using plot3. So for example, if you wanted to do something a little bit more fancy, like draw the lines and the magenta circles at the same time, right? We saw how to do this earlier in the 2D plotting tutorial. We could just turn the hold on, and then what we'll do is we will plot both the line and the magenta circles on top of each other, and now here we are. So we get our plot here of our upward spiraling elliptical helix with both the lines connecting the data points as well as the magenta circles showing the actual data points here. Great. So I think that is a fairly reasonable approach here and discussion here on the 3D plotting of lines here. So maybe what we should do here is to keep this simple, or to keep this delineated here, let's just go ahead and start a new cell and call this 3D lines here. And now what I'd like to talk about here is 3D surfaces, okay? But before we jump into 3D surfaces, I think we need to take a step back here and talk a little bit about the concept of generating a three-dimensional surface on a computer. So to do that, let's jump back over to the whiteboard. All right, so again, I think it might be useful to review what we talked about with 2D plotting, and then we'll look at the extension to 3D plotting. So you know what, let's go ahead and divide this straight down the middle here, and maybe on the left, let's talk about 2D plotting. And then eventually we'll get over here to the right and talk about 3D plotting. So again, we're just looking at some of the concepts. So if you remember here with 2D plotting, what we said here is a 2D plot, it's really an evaluation or a representation of some function f of x. And we want to look at all of the x values and what are the resulting y values. So again, the way I like to visualize this here is you have some function f here, right? And as inputs, or the domain, you have x. And as the output, you have y here. And all the plot of f is, it's really just drawing two axes here, right? You have x on one axis, and you have y, which is equal to f of x on the other axis. And then what you're looking to make is a representation of the relationship between the x's and the y's. Now, if you remember in a computer, we talked about how you're not able to actually get this nice continuous function. So instead what we did was we chopped up the domain x into discrete values and then evaluated the function at those discrete values to get distinct points, like such. And then we connected them all up together with a line. All right, so the question becomes now, how can this concept be applied to generating three-dimensional plots? So in a 3D situation, you still have a function f here, but now instead of a single input x, you now have two inputs. Maybe let's call it x1 and x2, which are somehow combined to generate a single scalar output y. So you can still graphically visualize this as having f, but now there are two inputs, an x1 and x2, to generate a single output y. So to plot this graphically, we see that two axes are not sufficient any longer. I need three axes. So along one axis is going to be x1, along the second axis is going to be x2, and now along the third axis is going to be the resulting output of combining a pair of x1 and x2. And now a 3D plot of this function is now a surface, right? It's not a line any longer that somehow overlays this entire domain here, which tells you what you get when you combine an x1 and x2 pair. So what I want to talk about now is how are we going to discretize it like we did in the 2D case? All right, so here's a cleaner version of those three axes, namely x1, x2, and f of x1, x2. So the first thing we want to do is let's consider values of x1 that we're interested in plotting over. So maybe let's choose two distinct points here. I've drawn them here as these green circles. Let's say we're interested in x1 values of, let's call it +1 here and -1. So now that we've discretized the x1 dimension, let's do a similar operation in the x2 dimension. So I'll discretize that and look at these green points here in the x2 direction. So these ones are located here at x2 of -2, x2 of -0.1, and an x2 of +1.7 here. So all we're doing right now is we're discretizing the x1 dimension and the x2 dimension, but we're doing it independently. We're basically picking points in x1 and x2 that we're interested in for this function evaluation. The next step is to take a Cartesian product of these two sets of discrete points to generate a mesh of x1, x2 coordinate pairs. Graphically, we can visualize this by drawing dashed lines through each of these green points and then generating a set of points wherever the dashed lines intersect. So I'm showing these intersection points as these red dots. And just to make sure we're all on the same page, let's go ahead and label each one of these coordinate pairs here. So for example, this one back here in the corner here, this is at a coordinate of x1 of -1 and an x2 of -2 here. Similarly, this one over here is at a x1 of +1 and a x2 of -2. And let's just go through and label each one of these coordinate pairs here. So I believe this one is at -1, -0.1. This one here is at the coordinate of +1, -0.1. This one here is at the coordinate of -1, +1.7. And this one is at the coordinate of +1, +1.7. So to reiterate, these 6 red points were generated by meshing the two sets of green points. This operation is actually fairly important in the process of generating a 3D surface plot, so Matlab provides a function called meshgrid to perform this operation. Now, we'll take a closer look at the function later, but I just wanted to call your attention to it now since it's the current topic of discussion. Now, we can simply evaluate the function f at each of these red points. So, for example, if we pass in the point -1, -2 to the function f, we can plot the output of that as this orange dot here. And we can simply continue this process for each of the meshed red points to get a series of orange dots which represent the function at each of these locations. So again, just to be completely explicit, let's label each of these. So this one over here, this is the function evaluated at -1, -2. Over here is the function evaluated at +1, -2. And here's the function evaluated at -1, -0.1, the function at 1, -0.1, the function at -1, +1.7, and finally we have the function evaluated at 1, 1.7. So at this point what we have is this series of orange dots which represent a three-dimensional point in space, which are effectively discrete locations of the surface we're interested in plotting. Now, we don't want just a series of points in space, we actually want a full surface. Well, 3 points define a plane, don't they? And a plane is a type of surface, so why don't we take these 3 points in the back and connect them with a triangle/plane? In fact, we can repeat this process for each series of 3 points to generate a discrete representation of the surface. So in a nutshell, this is how we can generate a discrete representation of the function f on a computer. Now that we have the concept down, let's jump back over to MATLAB to see how to implement this workflow. Alright, so back here in MATLAB, let's go ahead and first take a look at one of the simplest ways to generate a 3D surface in MATLAB, and that's the patch command here. So the patch command, it basically draws a triangle like we were talking about earlier. So all you need to do is define 3 points in space and it will connect it as a triangle. You know what, let's scroll a little bit up, and if you remember, this is 3 points that we made earlier and plotted them using a line. Well, what happens if we wanted to plot that same 3 points using a patch here? So I'll just go ahead and get them. And then what we can do here is all you need to do is start another figure, and instead of calling plot 3 here, let's call patch on X, Y, Z, and you actually have to give it a color as well. You know what, let's use magenta, just like we were doing in the whiteboard example here. So if we go ahead and run this, what we see here is patch is going to create, yes, basically take 3 points in space and draw a triangle here. So you see, this is one way we could go about creating a surface in MATLAB, is you can just go ahead and continually use patch over and over again by connecting series of 3 coordinates to make a surface. Now, while this is conceptually fine here, it's actually very, very cumbersome to do, so we'd like to look at a different routine to generate a surface here. So that's going to lead into our discussion here of the mesh function. So to use the mesh function, we need to implement the workflow that we looked at on the whiteboard. So let's start by defining the domain of the function we're interested in. So in other words, we need to define a 1D vector of x1 values and a separate 1D vector of x2 values. So why don't we use exactly the values that we had in the example here? So x1 will go from -1 to +1, and x2 could have values of, I think we had, what exactly were we using? I think it was -2, -0.1, and +1.7, something like that, right? Okay, now what we can do is we can create a mesh of these points using the meshgrid function. And recall, this is where we called your attention to earlier when we were drawing the dashed black lines and calculating where they all intersected. So with meshgrid, all we do is we pass it these two 1D matrix, 1D vectors, x1 and x2, and what it will return is, let's call it capital X1 and capital X2, which should be the meshed version of these two vectors. So let's go ahead and just run this so we can see what it looks like here. And again, we see here's x1 and x2, right? Those are our 1D vectors. But now capital X1 and capital X2 are effectively, right, those x1, x2 pairs here where we can use them to evaluate the function at. So for example, the 1, 1 element of x1 should match up with the 1, 1 element of x2 to give us a Cartesian coordinate of -1, -2, right? So that was one of those first red dots. I think that was in the back left corner of the graphics we were looking at earlier. So now what we're free to do is we can go ahead and evaluate the function at these x1, x2 pairs, right? All right, so to do that, let's just pick a random function. I don't know, maybe let's just make x1 times x2. That's our function here, f here. It just multiplies the two together. So now what we see is we're creating a matrix Z, which is effectively all of the function values at each of those corresponding pairs here. So again, let's run this code here and pull up x1, x2, and z. And I guess I can't fit them all up. Well, oh, it looks like we can fit all of them here, right? So again, the 1, 1 element of the Z matrix is basically the function evaluated at the location -1, -2, and etc. for all of these. So what we can now do is let's go ahead and plot this using the mesh command to see what it does. And what we said is mesh should basically be giving us these triangles. So instead of calling patch over and over on these triplet pairs here, mesh is going to do all of that for us. So in order to call mesh, I'm going to pass it x1, x2, and then the corresponding z heights here. Okay, and let's keep the code really simple for now and just to see what we end up with. So here's what we get. So we get this three-dimensional surface where if you rotate this around, you see it's basically a bunch of triangle planes connected together. So all mesh is doing is it's taking those orange dots that we had on the whiteboard and connecting them with triangle planes. Now, obviously, this plot is pretty ridiculous here because we have such a coarse mesh. So, you know what we should do is let's come back here and use something better here than this very, very coarse mesh. So let's refine this. Let's go ahead and maybe make this a linearly spaced vector, maybe going from, how about from minus pi to pi, and maybe let's use 20 elements here, and x2 here, let's make this also a linearly spaced vector going from, what do I have in my example here? Let's make this going from, how about, whoops, excuse me here, going from minus 10 to, how about 16, and let's use 30 elements here, again, just to show they don't have to be the same here. And we can evaluate these functions, and you know what, let's change this function to make it a little bit more interesting. Let's maybe make it cosine of x1 times x2. That might give us a little bit more interesting features. Maybe we'll add a little comment here, like call meshgrid to create a Cartesian product of lowercase x1 and lowercase x2. So again, make sure you keep in mind lowercase x1 and lowercase x2 are the 1D vectors, whereas capital X1 and capital X2 are the matrices which represent the Cartesian products here. So now, again, if we run this with mesh, we start to see something very reasonable, right? So now that we have a little bit finer mesh, you can see what's going on, right? So mesh is making this surface that's created out of a whole bunch of triangles effectively to represent this surface. So we get something that looks actually very nice. And again, we're free to go ahead and pretty up this plot if we want. So for example, let's go ahead and, you know, we can have the X label as X1, the Y label as X2, the Z label now as Z is equal to F of X1, X2. We can turn the grid on. We can add a title saying, how about using the mesh function? And yeah, I think that's pretty good here. Let's go ahead and run this. And yeah, here we go. This is looking reasonable. The one other thing that maybe I'd like to call to your attention right now here is if you go ahead and start rotating it, you notice down there in the bottom left of the figure, there's a two numbers being showed up, an azimuth and an elevation. So those are basically angles that if we put this in some orientation that we like, I don't know, let's pick something, you know, something like this maybe seems, you know, maybe we would like to view it from this angle here all the time. Maybe an azimuth of 35 and an elevation of 30 here. What you can actually do here with three-dimensional plots here is instead of having to drag and manipulate the plot to get the viewpoint you want, you can actually go in here and you can say view, and if you pass it an azimuth and an elevation, it will just rotate the picture to that viewpoint, so you don't have to do it yourself. So if you get an angle you like, go ahead and just write down the azimuth and elevation, and then call the view function, and it will basically display that from the desired location. So this looks pretty great here, but there are actually other functions in MATLAB that we can use to generate this surface as well. So let's take a look at a few of these right now. My favorite function for doing 3D plots in MATLAB is called surf. And surf operates very similar to mesh. In fact, it's so similar that we can pretty much copy this entire block of code that we use to generate a mesh plot here. And instead of calling mesh, let's just call surf here. And I'll change the title here so it's accurate. And we'll say that this is now using the surf function. So if I run this, we can compare what mesh and surf do compared to one another. So let's put the mesh on the left and the surf on the right, and you can basically see that they're very similar. Surf just does what mesh did, except it colors in each of these panels with an appropriate color here. So this looks great and all here, and I think we're starting to build some nice plots, but let's talk about some of the bells and whistles that surf has that maybe mesh or some of the other functions don't. So one of the things you'll notice here is that surf does draw black lines to kind of show the outline of each one of these panels. You can probably imagine that if you have a really dense mesh grid of points here, it's going to be very hard to see the actual colors coming through. You're pretty much going to get a big plot of black here. I mean, to illustrate this, let's crank up our mesh up here. So instead of 20 points, let's do 200 and 300 here. And if you run this again, you look at the mesh or the surf, and yeah, this is unfortunately it's pretty much all black. You can't really see it here. So to fix that here, maybe let's go back here to our original 20 and 30. And if you want to get rid of those black lines, what you can do here is just say shading interp. So what this does here, let's make a little comment here. This is gets rid of black lines in the surface plot. So here we go, let's run this guy again. And now we see we get this nice smooth surface here with no black lines here. Okay, so that's nicer, I like that. let's see, what else kind of things can we add to this here? Well, it would really be nice if we could have a map of what each of these colors meant in terms of their z-axis height. So, you could look at this thing straight on the edge here, and we see that, yellows are at about a height of 15, dark blues are down here at a height of, maybe minus 15, but it would be really nice if we had like a color legend or something like that to show what these are. So to do that, you add what's called a color bar. So you just go ahead and hit color bar here. I'll put a comment here, and this adds a color bar that acts as a legend for colors effectively. So I think instead of me explaining it, let's just run this again and you can see what it does. So you get this nice bar showing up on the end, showing you what the actual colors and their respective associated values are. So this is great, but let's see what else can we do. Let's make this a little bit more fancy. We can actually change the coloring scheme here. So if you don't like this orange to blue scheme, there are other maps that you can use here. So let's just say, I'm going to say help color map here. You get all this information. Let's go to the reference page actually for Colormap here. And you see Colormap is going to allow us to pick a specific different type of map. So if I just scroll down, I'll let you read this documentation if you like, but halfway down this documentation page, there ought to be, let me see, where is it? Ah, here we go. There's a whole bunch of all these different color schemes you can use here. So there's these things called, spring, summer, autumn, winter. It looks like a lot of seasonal colors. You know what? Let's try that. So what you could do here is let's add a different color map here. So let's say color map, how about winter? Let me just see. All right, and then if you run this again, you see that you get a different color scheme. You could say color map summer, get another color scheme, all right? Or you could now use some of these other maps by passing it in. So there's one called Jet. Jet is one of my favorites here. And Jet, we can specify how many levels of granularity we would like. So maybe let's do something small to start off with just 5 levels of granularity. And if you run this again, you see what we end up with is this map here where there's only 5 different colors here, or 5 different levels of granularity here. Obviously, if you want to increase this and make this a little bit more discerning, what you could do is just increase this. So I don't know, let's go up to 50 levels here. And you run this again, and we start getting this nice gradation here of the color scheme here. So again, this is actually a lot of fun, and a lot of it's able to customize your plot to be exactly how you like it. So there we go. That's how surf operates. Let's take a look at another way to represent this three-dimensional plot. How about looking at the contour function here. So contour is, I think the easiest way to look at it here is, let's just go ahead and again copy some of this code here, paste it down below, and again, instead of calling mesh, let's call contour here, okay? And I'll just change the title again, and let's run this. And actually I'm going to take away the view part. It'll make sense why I'm getting rid of the view here in just a second here. But if you run this, you see what contour does is it gives you sort of a two-dimensional iso map or contour plot of that function here, right? So again, it doesn't make sense to really rotate this. That's why I was getting rid of the viewpoint, right? Because this is really supposed to be a two-dimensional view of sort of isobars or constant levels of this curve here. So these are effectively level sets of the function. Contour has another sort of sister function called contour F. So if you want to see contour F, it's basically the filled version of contour here. So you see that it just basically colors in some of these sections here to give you a better idea of level sets. I kind of like the contour function myself here. So let's just go back to contour. Now, what's really cool is we can start combining some of these. So there's a function called surfc. So let's take a look at that here. Surfc, and what surfc does is, you know what, let's copy the entire block of code where we had for surf, paste it down below, and instead of calling surf, let's call surfc. And again, I'll change the title here to be surfc. And if we run this, what we end up seeing here is that what surfc does is it sort of combines contour and surf together. So let's see if we can look at multiple of these all simultaneously. I know this is probably not going to work very well because I don't have much screen real estate here, but you see here that what we end up with is that surfc is going to do the surface plot like you expect and then draw the contour plot underneath. So it's a really neat way to sort of visualize this function here, right? So I think this is making nice, pretty helpful, informative plots here to understand how this function behaves. All right, so now that we've looked at both lines and surfaces, maybe we would like to combine the two. So for example, what if this surface here represented, like, for example, like terrain of some mountainous region, and we would like to draw a line of a trail that goes over this surface here. So what we can do here is, let's go make another section that says, how about make a composite plot here. So let's go ahead and define some x1 locations. So maybe we'll say that the line here starts at the coordinate x1 of -1 and goes to +1, and maybe we'll use 20 spots. And the x2 locations here go from maybe, how about 0 to 10, and let's use the same 20 plots here. So the z values along that trail here is basically the function, right? It's x1, or cosine of x1 times x2. Right? And now what we can do here is start thinking about overlaying this line with the surface. So you know what? Let's just copy the code we had earlier here for generating a surface, paste it down here, and we see the one modification we need to do is if I want to make a composite plot with multiple things, I need to turn hold on. And then I'm free to go ahead and use plot 3 here to plot this line that we made here. And you know what, let's go ahead and make it, how about a magenta line here, and we'll maybe make it a little bit thicker here so that it shows up a little easier on the plot here. And again, let's change the title to be something descriptive here. How about making, or how about just call this a composite plot? Okay, and run this here, and here we are. So you see we've got the surface and the line overlaid one on top of the other here. And I think with this, we should hopefully be fairly comfortable now with making three-dimensional graphics, both lines and points, as well as surfaces or meshes in Matlab here. Things start to get actually really fun now here. For example, you know, as an interesting side note here, I think you guys are all familiar with the Matlab logo here, right? You see this little, it's effectively a surface here. So, you know, we have enough tools at our disposal now to generate the Matlab logo, or at least a reasonable approximation for that. So the logo is actually a, I believe it's an eigenfunction of a membrane. So you can just do this. So I think it's 160 times membrane of 1/100 here. So membrane, I'll let you read what that does, right? And it's basically used for generating this logo here. So what this is going to do is L is going to be a bunch of these height values effectively for the surface. So if we go ahead and you can actually use surf here, if we don't give it X and Y values and just give it the Z values, it will assume X and Y domains. So you could do something like this, right? You could say just surf Z. And if you plot this here, oh, whoops, sorry. You know what I need to do? I need to start a new figure. It's trying to draw everything on top of one figure. Let's try that again. All right. Oh, sorry, not surf Z, surf L. All right, that's what I'm looking for. Here we go. There we go. So this is looking like the surface, but again, we now have the tools that we need to sort of start cleaning this up to make it look a little bit more like the Matlab logo that we expect here. So first of the things we want to do is turn the shading to interp here, and let's also turn the color map to something a little bit more reasonable, maybe like autumn. Something like that. And now if you run this, here you go. This is starting to look pretty reasonable, right? Doesn't this look like the Matlab logo and how you can use it to manipulate things? So anyway, I hope this has been helpful for generating surfaces. Let's do a quick recap on what we covered in the tutorial today. So to summarize what we looked at today, we started by looking at how to generate 3D lines and points using the plot3 and scatter3 functions. We then covered the general concept of how to discretize a 2D domain and generate a subsequent discrete representation of a function on a computer. With this concept covered, we looked at the Matlab tools needed to implement this workflow, namely the patch, meshgrid, surf, contour, and surfc functions. Finally, we looked at how to create composite 3D surfaces along with 3D lines or points to generate interesting and descriptive graphics. So I hope this was helpful. If you enjoyed the video, please subscribe to the channel by clicking on the icon that should have just appeared on your screen. we'll have weekly videos covering more topics in MATLAB as well as other engineering topics of interest in the future. With that being said, I hope to catch you at a future video. Bye.